I'm Sean Rager, and this is my Lab 2 for Georgia Tech Physics 2 on the lines of charge experiment. This lab is a more accurate look into Lab 1, so we will start off by reviewing the procedures from Lab 1. Our problem statement remains the same across both labs. We've seen that in the lab, pulling one strip of tape apart from another causes that strip to become negatively charged, so our goal is to, as accurately as possible, calculate the charge on this negative tape. In the experiment, we created two U-tapes and then arranged them with one suspended above the other and made them close enough that the effects of the two charges on each other were apparent, and the tape on the top actually became floating motionless in the air. And so we can apply some physics principles to this precise situation to give us a good idea of how to calculate the charges. This starts off with the gravitational force, which is mass times gravitational acceleration. This force points downward on all objects with mass. Electrical force, F equals K times Q1, Q2 over R squared, with K being Coulomb's constant. And we can also see, without Q2 in this formula, this is also the formula for electric fields from a charged particle, which we'll be using a lot in our calculations later on. The principle of superposition comes into play heavily in this lab, as we will be comparing a number of iterations of electrical forces generated from charged particles on each other, and we will see this in a looped format in our code. And finally, Newton's third law, where we see two objects that come into contact with each other exert equal and opposite forces. We see this equal and opposite force heavily in our calculations of electrical force and gravitational force, balancing each other out and causing that tape to remain motionless. As we see, there is no net force because this object is not in motion, and therefore our calculations rely on balancing out these two forces to get an initial charge estimate. Our data gathered in the lab was that our tape length was 20 centimeters, mass 2 grams, and the distance between the tape of 0.3 centimeters. And here's our free body diagram once again, where we see that gravitational force and electrical force should balance each other out so that that top tape remains motionless and there's no net force acting on it. As for the improvements we've made to our model in Lab 2, we are now assuming that the U-tape has the same amount of charge, but it's evenly distributed along the length of the tape instead of being one point charge right at the center of the tape. We are still ignoring air resistance as there's no significantly moving objects in this lab. And now taking a look at our code, we initially started off by assuming that our Q remained the same from last lab at 1.4 times 10 to the negative 9 coulombs. But we can see this line of code was actually edited out as we came to a more precise calculation of Q later on, but we will see that with our model. We can also see that the charge of each sphere, each little individual point charge, is equal to Q divided by N, with N being the number of individual separate charges that we are dividing our tape into. Mass was divided the same way. Each little segment of tape had the total mass divided by the number of segments. We've used two nested for loops in this experiment to make sure we are calculating the results of every particle from one tape on every single particle of every other tape. And then at the bottom, we are summing all of these individual electric field vectors with each other using that law of superposition that we talked about earlier to come to our net electrical field and thus net electrical force. And here are our computational models. We can see the one on the top left uses the original charge that we calculated from last lab, and there we see the arrow of net electrical force is not even close to the arrow of net gravitational force. So we adjusted that value for part 2, or in later calculations, which brings us to the model in the bottom right, where we see electrical force now balances out gravitational force, just as our initial models had showed. And this shows how the number of N, the individual segments that we divide the tape up into, we can come to a more precise model by increasing the number of iterations and thus having more realistic models. As we know, there are a great deal more than 75 individual atoms interacting with each other in our tape. So the more iterations, the more accurate the model. We can't do billions because of the constraints of our coding software, but we can increase the number to make it more accurate. And now finally closing out with some conclusion questions. What if we had modeled each of our tapes as a single point charge and compare this to the distributed line charge that we had in this lab, and we can see that the charge is much greater that we calculated using the line model, 421% greater than when we estimated it as a point charge. And why do these estimates differ? Which value is more likely to be closer to the real value, and why? And they differ because of the two assumptions that we made at the start of the calculations by starting off our calculations and our models with different angles, one being the point charges directly balancing each other, and the other being the number of iterative segments that the law of superposition adds together, the effects on each other. We ended up with different results, and the line model is going to be more accurate, as we mentioned earlier. That is closer to how real-world forces between particles within objects interact. Their net force and their net field that they lie in are the sum of the interactions of all the molecules around them, and therefore the line model is more accurate. So that is the improvement to our original purpose of calculating the exact charge on a strip of charge tape. So thank you for listening and watching.